Good morning.
Good morning, Dr. Terrell.
Good morning. Good morning. Let's see, where am I? I'm on sharing screen. And I want to exchange these screens down here. Hope, Ken, Hector, Jean, Abby, Romeo, Tyler, Sue, and Vincent. Excellent. Oh. Okay. Oh, there we go. That's what I need. Okay. Can everybody hear me?
Yeah, we can hear you.
Let's see here. H. Vincent says yes. Good. Excelente. Alrighty. So no robot voice, right?
No robot voice.
Good. Excellent. Somebody say something. Say
Saying
hi,
something. Hello. Can you hear me?
I can't hear Abby. Shit. Let's see here. Okay, say something again.
Okay, I'm saying something again. Let me leave and join again.
Why does this keep happening to me?
Can you hear me?
There's something weird about the Windows audio drivers. There's something like
I don't think
strangely complicated about them.
Okay, can you hear me now?
Okay.
Oh,
Yeah,
okay.
we
So
can hear
other... Okay, sweet.
Well, we can hear you, Abby, but we don't know if Dr. Terrell can.
I see.
I do not hear anyone. Let's see here. That's probably not wise. Let me try undoing this.
Dr. Terrell, can you hear me?
Oh, you had me muted.
Can you still hear me?
Yeah, I got a thing saying that he asked if he could unmute me.
Abby, try saying something. I was picking
I'm still talking. I'm still talking. I think he has us muted, guys.
Hello, Dr. Terrell.
I would type it, but I'm putting in my contacts.
You just have to communicate by text, I guess. Okay, I can't hear anybody. Dang it. Anyway. Oh, wait. No, there you are. There we are. Now we're coming back.
Do you have us muted?
I don't know. I definitely didn't have you muted.
Because it asked me if I wanted to be unmuted.
Oh God, I don't know. There's too many mutes in series here. Okay, so let's talk about obvious crap. Can you all see the lecture notes page starting in vibrational spectroscopy?
Yes.
Excellent. So, so what I would like to do is talk about temperature first, right? Let's talk about this temperature column right here. And there's actually more to it here, isn't there? So if you want to talk about UV vis spectroscopy, there's a certain energy associated with that. And energy has this temperature equivalence through the Boltzmann equation, which is, let's see, this column here is connected through E is equal to KT, right? And if you associate a temperature just naively through this equation with the UV vis, you get about 140,000 Kelvin. So, you know, like surface of the sun type stuff. So what that means is that at 140,000 degrees Kelvin, there is enough thermal energy just floating around to excite a visible or an ultraviolet transition. And while that's kind of interesting, gee whiz, I mean, there's, you know, no place on Earth where these temperatures aren't typical, right? Except for, you know, possibly in an ICP type plasma or a flame, you know. Now, those temperatures are much lower, of course, they're a factor of 10 to 100 lower, but the transitions are still visible. Now, moving towards the infrared, you see, you know, the UV vis, the near IR, the mid IR, around 1,000 wave numbers. And then it's not until you get to, like, you know, the far infrared region here, you know, where we're around 300 Kelvin, that you can see that there's enough energy in the metric KT to excite group, you know, typical mid-infrared group frequencies. So what this means is that above this, at room temperature, these quantum states are generally in their ground state. So you can say, well, are molecules typically in their ground electronic state? Definitely. And they're typically in their vibrational ground states as well. Oops, sorry. So that's basically the point of all this, you know, is that there's all of the vibrational and electronic spectroscopy that we talked about so far starts with molecules in their ground state, and we're actually going to stay in that realm, right? Now, what we see in the infrared is vibrations and rotations, right? And basically, and generally as chemists here, we stay in the solid and liquid phase. If you're a physical chemist, maybe studying um, I don't know, atmospheric chemistry or something, you could get into here, but into the gas phase. But most analytical chemistry is done in the condensed phase here, and there are some rotational spectrum, mainly in liquid, but these just contribute to the width of the bands observed in the infrared. So they're basically not observed or not resolved in the IR or Raman. However, the solid and liquid phase vibrations are definitely resolved. They're broadened, but only to maybe say 5 to 25 wave numbers. Is typical for the width of an infrared or Raman peak that you would see from the condensed phase. And this is called condensed phase. So that being said, what are the infrared selection rules, right? And this is, we've spent a long time establishing the premier selection rule, which is that the photon energy equals the transition energy, right? And now what we're doing is we're saying, well, from the perspective of the molecular structure, what makes a particular vibrational mode infrared active? So let me add that point in here. So from a global perspective, delta E is equal to delta E for the transition must equal H times nu for the photon. Right? But from a oops. Oh, geez, what happened there? I like it. From a molecular structure perspective, then the way we explain it is this, and we can summarize it below. So we start with light, and light is an oscillating electromagnetic field, right? And we plot the electric part. That E field here is positive and negative, positive and negative. This is time here. and this is a particular point in space, right? And when this field is positive, it will act on the hydrogen atom in the HCl molecule, assuming that HCl molecule is aligned with the photon's electric field at the moment that they interact. It will act on it such that the force. Oh, it depends on whether we're using the. This is the chemist dipole here. Wait, no. If it's in, that means that the force is like this, and that means that this is the negative end, and this is the positive end of the dipole. So this is a physicist dipole, and what will happen is that because the electric field strength, it's basically superimposed on the molecule here. The negative end of that dipole will feel a force moving in the upwards direction. The positive end of the dipole will feel a force moving in the downwards direction momentarily, and then that force will flip, right? And then they'll feel the opposite force, right? And and this alternates, right? But if we consider a zero dipole moment, there's always zero force, right? So there's no way in first order for light to excite the vibrational modes in, say, dinitrogen. So the selection rule for optical absorption of light by a vibrational mode is that when a vibration causes a change in the dipole moment, i.e. a dynamic dipole is needed, then that mode is IR active, that is, it is observed. Any questions about this so far?
None for me.
Okay, all righty. Make me some. Good. Thank you. Excellent. So rotational is a similar question, where there's when the electric field of the light is positive here, then it will attract the negative end of the dipole and repel the positive end. And it's the same for rotation. A molecule simply has to have a permanent dipole moment, and then it will be rotationally active. So, for example, carbon monoxide has a small but non-zero permanent dipole moment, and you can see the rotational fine structure. So each of these bands is a distinct rotational transition. And then this entire side is for the well, actually, all of these bands here, all of the bands, they share delta V equals +1.
Will it always be symmetric like that?
So that's a very good question. So before I get too deep in this, I should actually explain what the hell we're talking about here, right? Thank you, Matthew. So this is carbon monoxide in its gas phase. That's an easier experiment to do than the condensed phase carbon monoxide experiment. That's got to be very cold. But in the gas phase, you see you can see the 0 to +1. It's V equals 0, 2, V equals +1 everywhere, right? So that's 0 to +1. And then on the let's see here, on the low energy side, you see the delta J equals -1. On the high energy side, you see the delta J equals +1. And then there happens to be no delta J equals 0 peak. The delta V plus delta J, and when this is +1 and 0, this is forbidden. So this type of fine structure is only observed in the gas phase. Right. And so, for example, what would the gas phase rotational and vibrational spectrum of dioxygen look like? Well, to first approximation, oxygen has O2 has what dipole moment?
It doesn't have a dipole moment.
Exactly. So, can it have a rotational spectrum?
No.
Yeah, didn't they say it needed to have a permanent dipole moment in order to have a rotational spectrum?
Yes, it does. And how many vibrational modes does the O2 molecule exhibit? Okay, so this is actually a very good place to start thinking about vibrational modes, right? Let me just see whether that's where we're going. Yeah. We can consider a diatomic molecule, right? And a diatomic molecule, in order to analyze the modes, we're basically going to consider just along the OO bond axis, the number of possible ways that you can independently move these atoms, right? This is the number of ways that you can move the atoms. You can move them both up, both out, or both to the right. This is out, and these are the three Cartesian axes, right? Or you can move one up and one down, one up, one down, or one in, one out. Or there's actually no way to represent this last one in the z dimension. So this is basically what, and then for the vibration that you get is when you move one to the left and one to the right, right? These are these are the only ways that you can move each of these atoms along a single Cartesian axis. And you can see here, obviously, that for O2, for example, it will have one mode of vibration. Okay. because if they both move the same direction, that's not vibration. That's translation. That's moving the whole molecule, right? If they move opposite directions, that's rotation, and this is called a pseudo rotation. It's not observed spectroscopically. And then if they both move opposite directions, that's half of a vibrational mode, you know. But since the light is oscillatory and they exchange energy, then it becomes a vibration.
Is the
He says,
vibration affected by the bond length?
"Oh yes, oh yes, yes it is." So, so linear molecules have actually only 3n minus 5 modes of vibration. Where
Yep.
n, n is the number of atoms. And nonlinear molecules have 3n minus 6, right? So if n equals 2, it's got to be linear. So, you know, this is 2 atoms slash linear, and then 3 atoms slash nonlinear or higher is 3n, or 3, if they're nonlinear, 3n minus 6. If they're linear, that's 3n minus 5. And I was confidently stating to myself once, oh, there's no examples of linear molecules of 4 atoms. But then I was like thinking, oh, geesh, there is a very good example of a linear molecule with 4 atoms, which is H, C, C, H, which is acetylene. And I was looking up the vibrational spectrum of acetylene this morning, but I couldn't find it, unfortunately. Maybe I can, well, you know, I probably can't do that one until summer. Okay, so let's think about a slightly more complicated molecule, 3-atom molecule, CO2, right? Is CO2 linear or nonlinear? Let's see, who's got their microphone on? Abby.
Yes.
Yeah.
What are you asking?
Is CO2 linear or nonlinear?
It's nonlinear.
Yes. Yes. CO2 is, yes, you're right, Abby. CO2 is perfectly linear.
Oh yes, that is totally what I said. Sorry.
Good. So if while you're not actually talking, if you could mute your mic, that would be
Yeah, sorry,
awesome.
my hands were preoccupied.
No, it's okay. Thank you. There we go. It's just a little bit less background noise from me and probably others. So, so CO2 is linear, and then so it has 3. What is the n value for CO2?
3.
N equals 3 or CO2, right? And yes, that's true. So it's 3 times 3 minus minus 6, right? Yes, nonlinear is minus 6. I always get that confused. 3 times 3 minus 6
Minus
is
5.
Oops. Oh, right. Sorry. Oops. It's like a self-fulfilling prophecy because it's linear. Then linear has 3n minus 5. CO2 is linear, so 3 times 3 minus 5 is 9 minus 5, which is 4. And when you think about these, it's got a symmetric stretch here where the carbon atom stays still and the oxygen atoms move out. It's got an anti-symmetric stretch where the one oxygen beats against the other carbon and oxygen. And it has actually 2 bending modes, right? And the bending modes can be up and down in the plane, or they can be plus and minus out of the plane, right? And who can tell me what, if this bending mode is 666 wave numbers, who can tell me what the bending mode of this guy is? Hopefully someone non-religious who's not afraid to speak the mark of the beast.
Well, it's going to be pretty much identical, so it's also going to be 666.
Yes. Thank you, Matthew. It is the mark of the beast. 666 wave numbers, exactly. So now, this mode here, question, is it infrared active or not? And I gave away the answer here, it's IR inactive. Because as even though it has individual bond dipoles, right? The carbon is relatively positive relative to the oxygens, right? This is sort of delta minus, delta plus, right? This symmetric mode has no associated dipole moment. Does that make sense to everybody? I'm sure there's a good number of people for whom that doesn't make sense. Let's see. Kenya, can you explain why the symmetric stretch of CO2 has no associated dipole? Sue? Oh, Sue. Okay, it's open. Who wants to explain why CO2 has no associated dipole? CO2 symmetric stretch has no associated dipole moment.
It's because it is symmetrical. Both of them pull equally on the carbon, but in the like opposite, perfectly opposite direction, so it cancels each other out.
Exactly right. Exactly right. Exactly right. Yep. Very good. So now everybody should be able to answer that question on an exam. So I mean, and this is like P-Chem for babies and inorganic chem super light, you know. So this is one that you got to be able to express on an exam. You know? Just that simple thought that even though the bonds have dipoles, they're collinear. And yes, Catherine, thank you. Good job, Abby. They're collinear and they cancel exactly. So now, how about the antisymmetric stretch here? When this bond is short and this bond is long, where in what direction is the dipole moment of this molecule? Let's think about that question here. So let's draw, actually, let me just erase all this nonsense. And I'll draw it up here. In an exaggerated form, but let's put the delta minus, delta plus, right? let's say that the molecule is now in this horrifically distorted antisymmetric mode. And if I asked you the question, what is the dynamic dipole of this stretched form, or what is the dipole moment of this stretched form, what would your answer be? So this is a little bit more subtle because the charges are all equal, but the dipole moment is going to be
Is
like
it
that.
over
Mhm.
to the
Sorry?
right? To the one with the longer bond?
Right, exactly. That's right, Kenya. Because the dipole moment mu is equal to Q1, Q2 times R. So to the extent that these partial charges stay the same during the vibration, the dipole moment on the right-hand side will be much larger. Well, will be larger than the one on the left. So this is moment 1, this is moment 2, and then the net moment is going to be just the linear sum of 1 and 2. So basically, that means that on either pole of this stretch, there's an equal and opposite dipole moment. Therefore, it's IR active, right? And the bending modes are also infrared active because if you have this mode, then you've got minus and plus. And so the dipole moment from that will be to the left. I'm sorry, the chemist dipole moment will be to the left. The physicist dipole moment will be to the right. Let's use the physics dimension. So, but these two modes are called degenerate because they are essentially the same thing. Just there's just a change in perspective, basically. And so these are not distinct modes in free space. So there are basically there should be two bands observed. So 3 times 3 minus 5 equals 4, but we have 4 minus 1 because one mode is degenerate.
-6.
I'm sorry, darn it. Wait, didn't we say it was? No, we just said CO2 was linear, so it's minus 5, right?
H2O down there, though.
What? Oh, sorry. H2O, that's right. 3 times 3 minus 5. Matthew, could you just start teaching the course for me, please? I am so sucking here.
Wait, Dr. Terrell,
Yes.
hydrogen isn't it not, wait, isn't it
Yeah.
not linear? It's bend, so wouldn't, oh yeah, so it would be 6, right?
Right. Actually, let's see. So it's nonlinear, right? Let's just go through this one by one, right? So it's nonlinear, so 3n minus 6 here, yeah? So yes. So let's see here. H2O is nonlinear, so this should be 6, right? Is that right, Matthew?
It is.
Okay, so 9 minus 6, that's 3 modes, right? There's no degenerate mode because it's not CO2, it's H2O, right? So there's the symmetric stretch here, right? There's the anti-symmetric stretch, which is, and I don't know where the friggin' oxygen molecule goes here. And then there's a bending mode like that. Now, let's go ahead and predict which of these modes will be infrared active? So first of all, does H2O have a permanent dipole moment?
Yeah.
Yes. Okay, cool. Now, that permanent dipole moment is the sum of two dipole moments, two bond dipoles along each of the oxygen hydrogen bonds, right? So the permanent dipole is like that, right? So there's the permanent dipole, right? Now, if we make these bonds longer, this permanent dipole gets A larger or B smaller. So if the OH bond lengthens, the permanent dipole gets either larger or smaller. And so which one of those is it?
Larger?
Yes, exactly right. Because, you know, we've got delta minus, delta plus. As long as those partials don't change very much, then the individual bond dipoles increase in magnitude and their sum increases in magnitude. So that means that this mode of vibration, where the OH bonds are stretching symmetrically, is active, right? Now, the antisymmetric stretch, who can tell me if this one is active or inactive and why?
It's probably still active, right? Because one of the bonds would be longer than the other one,
Mm-hmm.
also.
Yeah, so if this bond gets super long and this one gets super short, right, then the net dipole, right, has gone from this direction to this direction, right? And then on this, when that reverses, when this guy comes in and this guy goes out, then the net dipole moment is aligned more with this bond, with the second bond here, right? And so the net dipole moment shifts to the right. And that is a description of an active, an infrared active mode, right? So last but not least, how about the bending mode of H2O? Is that active or inactive? In the infrared? Hector, I haven't heard from you in a while. I guess that wasn't actually a question. Hector, is the bending mode active or inactive? This is the bending mode.
I'm gonna say active.
And you are going to say correctly because the dipole moment goes from that to that, right? During the stretch. So this guy is also active. And you know, as the molecules get larger, more and more modes get active. So that's, A, because it's easier, and B, because it's kind of like simpler. We pick on these super small molecules to start with. And then after this, it's just a big old jumble. And and uh, and pretty much all modes are active. And for large molecules like biomolecules or something, like 10 atoms or more, very few people talk about individual modes, because individual modes involve all atoms, and all atoms moving or staying perfectly stationary in some kind of symmetric mode. It's kind of awkward to analyze for large number of molecules. It can be, and it is the physical basis, but mostly what we do there is we start to break them down into what are called group modes. We'll talk about group modes very shortly here. But so to see more than 3n minus 5 or 3n minus 6 mode bands, it is possible that you can observe what are called overtones. And and an overtone is a delta V value of plus minus 2 or plus minus 3. And for example, there's a third overtone of water in the near infrared, and it's very clear around 1,000 wave numbers. But these are less common, but they tend to be weaker, but they can be observed. Oops. Okay, and then a combination band here is where you see the sum and the difference of two frequencies. And don't ask me to visualize that shit. I don't even know. I think it can be visualized fairly easily, but it's a little bit out of my wheelhouse. Now, and this is one way where, through physically, realistic mechanisms, you can see more than the 3n minus 5 bands you typically see. Now, it's also really common that you're going to see fewer than 3n minus 5 bands. And one way is if the frequency is not in the 400 to 4,000 wave numbers range of a typical FTIR. And this is 4,000 is really the upper range for a strong, say, H carbon hydrogen or oxygen hydrogen band. So it's more typically below here, and this would be for heavy atoms. But if the frequency is not in the range of a typical FTIR, then you don't see it. And it may just be too weak to observe. Could be just have a very small dynamic dipole, and so it's not observed because it's so weak. It may be broad. It may overlap another band, or it could be part of a degenerate set, or like
heavy.
Sorry.
How heavy is heavy? You said 400 for heavy atoms, like.
Oh yeah, so like chlorine we still see, but like bromine and like a lot of the heavier atoms, like on the last below the first 3 rows of the periodic table, it's hard to see the spectra of those atoms and molecules because the frequencies are so low. Then I'll explain kind of, I can discuss that in a sec. So just hold on. I will get to that momentarily. Yeah, it's a good question, and then also it could be forbidden. So, because there's no dynamic dipole, right? Now, typically for larger molecules, larger than say 6 atoms, most molecules have many atoms, say greater than 5 or 6. You're talking about like 99.99%. That means they have many modes, and some modes are very complex, right? And so we typically don't analyze them actual mode by mode, but we just simply pick off the functional groups that are on the mode and say, well, let's say you can take the asymmetric stretch or the symmetric stretch of a methylene. This is called a methylene, right? And you can say, well, this has a dipole moment, and if there's a large molecule out here or a small molecule, that only makes a very small change to the frequency where this particular mode is observed, where the predominance of the motion is between this carbon, this hydrogen, and this hydrogen, right? So this mode, this symmetric methylene stretch, is simply, it's always observed when that functional group is present on a molecule at approximately 2853 wave numbers, And then there's also an antisymmetric mode, a little bit higher frequency. Then there's some other CH modes, right? There's a scissoring mode. There's a wagging mode. There's out of plane bending. It's like this is in out, this is out and in, this is, anyway, I don't know how to describe this shit. You get the idea. These guys are moving in this plane. These guys are moving out and in, and then these guys are moving together left and right, So, and these all just have different frequencies and intensities, And so for most analysis, you just want to say, does it have this functional group or not, for identifying a molecule? Like, for example, like we do with the NMRs, like, is this vibrational spectrum consistent with this molecular structure? Then you can say yes or no based on the presence or absence of these group modes or these group frequencies, right? And I like the description of this type of thing by my friend Steve Woodward as a pleasant fiction. There are no group frequencies, right? But there are no exact group frequencies, but there are approximate group frequencies. And so when you say, this mode is 2853, that's not true. But to say it's approximately 2853 is true, because any molecule with this functional group, carbon, 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 and then 2 hydrogens here, will have a mode around 2853. So it's just not the exact same frequency on all molecules. Okay, so have I beaten that horse to death? Yes. Excellent. Thank you, Kenya. Hopefully that makes sense to everybody. Now, this is just a stupid ass table. Don't worry about it. Now, group and other frequencies can be calculated approximately. This is P-Chem ultralight. Any Hooke's law oscillator, like 2 atoms connected by a spring, such as I'm depicting here, they can be approximated in terms of their force by Hooke's law. Hooke was a strange guy, contemporary of Newton. And I don't know how he got his name on anything, but he got Hooke's law. And no, I love it. I love it. In the 1600s, you could get your name by deriving an equation as simple as F equals ky. But there it is. And if you plug Hooke's law into Newton's law, F equals ma, right? Then F is equal to ky, and ma is equal to m d squared y dt squared, right? Then this is a second order differential equation which can be solved very simply with a cosinusoidal term for y of t, right? Y of t is cosinusoidal there. There's a pre-term, and then there is a term inside the cosine, which is Vm, which breaks down to 1 over 2 pi times the square root of k over mu, where mu is the reduced mass of the oscillator. M1 times M2 over M1 plus M2, right? And so units of mu are just whatever unit of mass you have. So what does this mean? Well, this is the classical approximation of a classical oscillator frequency. And the frequency here is related also then to the frequency of light, which excites it. Right? And E equals V plus a half times H nu. And nu is equal to 1 over 2 pi root k over mu. So basically, this comes out to, delta E is the photon energy, is equal to delta nu times HVM, right? Is equal to plus minus 1 times H over 2 pi times the square root of k over mu, right? And this is equal to H nu optical. So this is nu physical, and this is nu optical. And that interesting correlation always holds, right? And so whenever you have this similarity, then you can have a quantum transfer of energy. And since nu is equal to C nu bar here, sorry about that guy up there. It's probably correct in your notes, but since nu is equal to C nu bar, then delta nu bar or nu bar is sensitive to K and mu, right? K is the bond strength. And mu is the reduced mass. So going back to Matthew's question, I would like to throw out a general question, which is So when actually is a mode low frequency. Right, so if this is the equation for a mode frequency right here, right? No. So H never changes, right? 2 and pi, they're constants. So square root of K over mu must be low to observe a low frequency mode, right? So under what practical circumstances is square root of K over mu going to be smaller?
When mu is large.
Exactly. When mu is large. Exactly right. So when the mass is large, or alternatively, when somebody other than Matthew, for example, Abby or Kenya or William,
When K is small.
when K is small, exactly. So if
I
K
put it
is
on the chat.
what? Yeah.
I
So
said I put it on the chat.
I see it. Excellent, excellent, excellent. Large mu, low K. Exactly. So low K corresponds to what type of a bond? A weak bond or a strong bond?
Weaker since it's the bond strength.
Exactly right. Exactly right. Exactly right. You know, technically, it's the restorative force of the bond, right? It's not the total bond enthalpy, but since all chemical bonds are within a factor of 2 in terms of their total length, you can relate the K value to the bond enthalpy, you know. So those are what we typically think of the bond strength is the amount of energy that it takes to dissociate a bond. But yes, so for weak bonds and for high masses, there tends to be a very low oscillator frequency. Right? So what about the bond between potassium and bromide? KBr, right? What type of bond exists between K plus and Br minus?
Ionic.
Yes, it's ionic. So, although it's probably not typically widely advertised, is an ionic bond stronger or weaker than, say, a carbon-carbon bond?
Stronger.
I'm gonna say stronger.
These are all good guesses, but they happen to be wrong. So it's a little bit weaker than a carbon-carbon bond, right? And the masses of K plus and Br minus are quite a bit larger than the corresponding masses of carbon atoms. So therefore, KBr as a material will have only low frequency modes. Therefore, KBr KBr is infrared. So let's answer this question. KBr is IR opaque or transparent? Which of the two? So
Wait, actually, can you clarify the difference between those two? Like, will transparent not be visible, and then opaque would be slightly visible?
okay, yeah. So let me add another word here. So let's say mid-infrared. KBr in the mid-infrared, is it opaque or transparent? Opaque means that light does not go through it. Transparent means that light does go through it.
I think I'm gonna go with opaque.
Okay, alrighty.
Because if it doesn't go through, then it's not going to have like a wavelength that it shows up, right? Confused.
Right. So it's a good point to be confused, right? Because you kind of go through this process a few times, and what we'll see is that if that quantum transition is allowed, if this vibrational transition is allowed in the mid-infrared, then it will absorb that frequency of light, right? And so in the mid-infrared, that's around 2,000 wave numbers, 1,000, 2,000 wave numbers. You have to say, is there a mode by which KBR can absorb mid-infrared light? And because of the high mass and the weak bond, the only modes that exist for KBR are all yes, exactly. They're all very low frequency. So the higher the mid-infrared, the very far infrared, yes, it's opaque. But in the mid-infrared and the far infrared, and all the way through the visible, KBR is transparent. So in the mid-infrared, KBR is infrared transparent. Does that make sense?
I think so. Because it's not absorbing any of the light, it's just going through it.
Exactly right. Exactly right. It's kind of like, what is a cell phone but a high frequency flashlight? When you call somebody on a cell phone, you're just you're translating the sounds into the series of pulses, these light pulses that the cell phone emits, right? Now, the reason that these light pulses can get all the way to a transceiver tower is because they are at a frequency where the universe is completely goddamn transparent, except for metals.
Well, it's transparent to our eyes.
It's also transparent to this frequency of radiation, right? Because the cell phone transmits in these microwave bands of radiation. They're narrow microwave bands of radiation, but wood and all these plastic and drywall and roof tiles and rock and cement and all these things are transparent. They're like glass, like a very clear glass to these microwave radiation frequencies, right? Because there's no modes by which those molecules and materials, so these large molecules, can interact with that type of radiation. So the radiation just goes out, and it spreads all over the goddamn universe. It gets to the tower. The tower somehow sees this little blinking flashlight and focuses on that radiation, and then picks up the conversation. So that is a completely unwarranted transgression of my duties here as a professor to teach you spectroscopy. But it has to do with the fact that at different frequencies, materials can be transparent or not to electromagnetic radiation, light, which is the same damn thing in the radio frequency as is in the optical and the gamma ray frequencies, right? That materials, if they're transparent to that frequency, because they have no modes that can interact with those frequencies, then you can use those for telecommunications, blah, blah, blah. So let me wrap this up here. So let's see here. Molecules vibrate, right? When their atoms move back and forth relative to each other and preserve the center of mass, actually. Vibrations come in certain modes that involve the whole molecule. And modes where the molecule has a change in dipole moment are IR active, right? And the higher the mass, the lower the mode frequency. The stronger the bond, the higher the mode frequency. In complex molecules with many atoms, some individual parts behave as though they were independent. These are called group frequencies. And group frequencies allow you to identify functional groups within a given molecule. And that, my dear students, is all I wish to say today on this subject. Are we okay?
Yes.
Yeah.
Yeah. Yeah. I wonder what ye means. Oh gosh.
E means yes.
Ye means yes. Okay, cool. Okay, hold on. Okay, got it. Okay, so I will come on to Zoom again at 10 o'clock, and I will be available to help folks with their lab reports if they want help. And I'll try to set that meeting up so that you can share your screen with me so I can look at it if you won't. But otherwise, there's no lab today because we're sort of piling up the lab reports. And thank you for those of you who've gotten UV Viz in. That's awesome. And for the large number of you who have not gotten the main lab report in, please do that because you're not going to be able to pass the class without it. Okie dokie.
Bye, Dr. Terrell.
Bye. Thanks, everybody.
Bye, Dr. Terrell.
Bye.
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 Dr. Gerald,
Catherine.
hey, did
Hey.
you get my message?
Yes, I did. I answered your message.
Yeah.
Okay, I'll see you soon, okay?
Wait, no. Talk to me right now.
Okay.
Did you see the one that I circled? Are we supposed to do that part for the report?
Yes. Yes, you are.
Yeah, we are.
Yeah.
Oh, okay, because that part
You
I
need some
think-
help with it?
yeah, I think so because remember as you look at the thing that I sent you,
Mhm.
to get the ppm and the signal, that's from the chart or the graph, right?
Yeah, it's all graphed. I mean, some of it's graphed.
Yeah, but how do I get the B1 and B0?
Oh. Well, they just come out of Linest, right?
Yeah, but see, like, wait, I tried to do the Linus part, but it's not like I couldn't get it. I only got one number for the
Okay.
slope.
Oh, got it. Okay. So I'll I'll look at your report and then we can fix that.
Oh,
It's
okay.
it's a control shift enter thing.
Control Shift Enter, because that's
Yeah.
B1 and B0, right?
Yes.
Oh, okay.
Yeah. Yeah. Let's talk again at 10. Okay.
Why so late? Why not right now?
Because I've got to go right now, but we can come back in an hour at 10 o'clock and we can talk about it. Okay.
Okay, you're gonna send me the link.
Yes.
Okay,
Yes.
talk
Okay.
to you later
Talk to you
then.
again. Okay. Bye-bye. Sorry.
Bye.
Bye.